Everybody, welcome to yet another online lecture for Math 127 Elementary Cryptography at Christopher Newport University. Today we are going to be talking about what are called Diffie-Hellman schemes. All right, last class we saw the exponential cipher. Okay, the idea behind the exponential cipher was reasonably straightforward. We fix a modulus n, which should hopefully be very large and prime or close to it. And then we choose two numbers. Well, we choose one number, k, which is going to be our encryption key. And we choose it so that it is invertible modulo the Euler phi of n. All right, so we find k and we find its inverse j. To encrypt, we take our plain text, we raise it to the kth power, reduce it mod n. That gives us our ciphertext. And as we saw, if we take the ciphertext and we now raise it to that inverse, it will recover the plain text. Now, the remarkable thing about this is that this is incredibly secure. All right, so to give you an idea, let's look at essentially what would be a known plain text attack, which we've seen time and again has been kind of a weakness of various ciphers. All right, so we have Alice and Bob, and they're communicating, and let's just say we managed to get out of Bob the information that 1293 gets encrypted as 4,977, and we also get the modulus out of it, 7919. Okay, so to find the encryption key, once we find the encryption key, we can find the decryption key, we would need to solve this equation. 1293 to the k is equal to 4,977 mod 7919. In standard arithmetic, we would use logs, and it would be easy. It would take you all of a minute at most to figure out what k is. But standard arithmetic and modular arithmetic are very different here. There is no known fast way to solve this kind of problem in a general modular system. Basically, our only option is to go at it by brute force, checking one number after another. Well, if I'm working with a very large modulus, that will take way too much time. Okay, so this is good. This gives us a very secure cipher. The cipher itself isn't particularly interesting, but what we can do with it, though, that's where it gets very interesting. All right, so let's see where we're at right now. Okay, at the beginning of the semester, we talked a little bit historically about some of the older ciphers. One of the oldest ones in sort of use that we know of is the at-bash cipher. Then there's the Caesar cipher from the 1st century BC. We saw some basic ideas with monoalphabetic ciphers. Then there was a big jump with the Vigenère cipher in 1553. We saw the one-time pad is the ultimate sort of secure cipher. It's the Vigenère sort of twisted to be incredibly long and incredibly random, and remains today to be basically the only unbreakable cipher out there. We haven't talked about the Enigma machine yet, and I'm not certain we're going to get a chance, but hopefully we will. This came out in the 1920s, clearly lasted through the Second World War, at which point it had been discovered to be actually quite weak. But that brings us to this, to item number 6, new directions in cryptography. In 1976, two computer scientists, Martin Hellman and Whitfield Diffie, published this paper, and it set up a challenge for the cryptographic community. We're going to talk about the 3 problems that they set out, one of which they managed to solve, and then a couple of others that got solved in pretty rapid succession. One of these things led to what's called the RSA algorithm. This is what's known as a public key crypto system. Everything we've looked at so far is what's called a private key. We'll talk about the difference between them. Diffie and Hellman set out the idea of a public key crypto system in their paper. 2 years later, Revest, Shamir, and Adelman, hence RSA, came up with a solution to it in 1978. there is record that the British Secret Service had an earlier formulation even before the Diffie-Hellman paper in 1973, but they had never actually implemented it. Okay, so as I mentioned, we've been talking about private key crypto systems. All right, they have a couple of shortcomings. One is those keys are exactly that. They have to be kept private. This leads to potential security issues. All right, so first thing is initial setup. All right, so you have to set this thing up where everybody has these private keys that have to be secret, that have to be distributed between parties that are going to communicate. Now, if your parties are close to each other and there's not very many of them, that's easy. If they're spread across the world and there are millions of them, like there are in networks, that's considerably harder. The other thing is that we've seen with computational power, keys have to be replaced. You know, what was secure 1,000 years ago is nowhere even close to secure now. What was secure even 3 years ago isn't secure now because computational power increases. All right, the other thing is that private keys, they're inefficient when you've got multiple parties. You have to somehow get it to everybody. All right, if you have a really large network, it becomes kind of impossible if everybody's got their own private keys. All right, so Diffie and Hellman, in their paper, it's actually quite a hilarious paper to read. So it came out in 1976, and they, in the sort of opening paragraphs, they talk about, well, you know, people are getting more computers these days, and we can imagine a time when they are networked together and they communicate with each other. And so we're going to need to figure out how to do that securely. Okay, so Diffie and Hellman set out 3 sort of challenges to the cryptographic community. All right, first is what's called a key exchange. So what a key exchange is, we need a way to determine a private key where the parties are communicating over some sort of public channel. Sorry for that chime. That was an email coming in the background. So the idea being here, again, if your parties are close to each other and can talk to each other, this is easy. If they're on opposite sides of the country or the world, you can't get everybody together to secretly come up with a key. You have to be able to send your communication out where everybody could possibly intercept it and still have it be secure. All right, the next thing that they suggested was an idea of public key cryptography. Okay, rather than having this secret key that only the people who are communicating know, we switch it up. There are going to be keys that everybody knows. So everybody's going to have a public key and a private key. The public key is what people will use to communicate with them, and the private key is what they will use to decrypt those communications. So the idea there, though, is that while there will be these private keys, they won't be shared. They'll be personal. Again, sorry about that. They also realized as we start moving towards more digital communication, we're going to have an issue with authentication. Okay, when somebody is communicating online, you don't see them. All right, so how do you know you're speaking to who you think you're speaking to? It could be somebody impersonating them. All right, now one of the ways we've always sort of ascertained whether something, we've used signatures. We need an idea for a digital signature so that we can authenticate who it is that we're communicating with. Okay, so Diffie and Hellman, when they put out their paper, they raised these challenges, but frankly, they actually solved one of them along the way. Okay, so they came up with an idea for this key exchange, i.e. communicating over public channels that everybody can hear and listen to, and somehow coming up with a piece of secret information. Before we get into the details of it, I want to give you a model that is often used to describe how a secret or a key exchange works. Okay, so what we do, this is called the paint model. All right, so we have Alice and Bob. They're going to come up with a secret paint color particular to the two of them. What they're going to do is they start with some common color. In this case, it's kind of a brownish color. All right. This is public knowledge. Everybody knows what common public color is. Okay. Now, Alice and Bob then take that common color. They come up with some secret colors of their own. Alice has a secret color. Bob has a secret color. They then, in private, take those secret colors and they mix them with the common color. All right, so Alice has some color. She's mixed it in, gets this kind of purple shade out. Bob takes the common color. He mixes his one in and he gets kind of this orangish color out. But then they exchange those mixtures. So Alice sends her mixture to Bob. Bob sends his mixture to Alice. All right, so now Bob's has hold of this kind of purple mixture, and Alice has the sort of orangish one. Well, then they do what they just did again. They add their secret colors. So whatever Alice added here, she adds again. Whatever Bob added here, he adds again. All right, so this last color here, it has the common color, Alice's color, and Bob's color, and then it all gets mixed together. This one has the same thing. Okay, it got added in different orders, but it doesn't matter. They all get mixed together. They're the same color at the end. They are both they both have this common color, and that's private. All right, now, we started with this common public color and we ended with a private common color. Now, you might say, well, you could just undo it. All right. So we know that we started with something brown for Alice and we ended up with something on the kind of the purplish scale. So probably a blue got added in. But which blue? It could be a bright one. It might be a slightly less bright one. And if you've ever tried to match paint colors, it's incredibly difficult. All right, so you could try to do the same thing with Bob, but again, who knows? There's umpteen different ways to do it. And with so many options and no easy way to do it, you can't, at some intermediate step, undo the process and find the secret colors. Those are secure. All right. Couple of things, well, apparently 3 things to note about this. Alice and Bob were both necessary in order to create the private. All right. Alice couldn't do it on her own. Bob couldn't do it on his own. The other thing is, they don't need to know anything about each other. Alice doesn't need to know what Bob's secret color is, and Bob doesn't need to know what Alice's secret color is. They don't need to have any communication other than that exchange of the paint color. The next thing on that is that both Alice and Bob are also bound by that same problem. So Alice is in possession of the common color mixed with Bob's color. She can't separate it out and figure out what Bob's secret color is. It's still secret, and likewise for Bob and Alice. Okay, so now, paint aside, let's look at how we would do this mathematically. Okay, so Alice and Bob are going to try and develop a common secret key. We shall call that K. The general idea: Alice decides on a private key, we shall call K sub A. Bob decides on the same thing, and he calls his K sub B. There's going to be some common public key, we shall call it M for the moment. Now, what they want to do is come up with some way to combine the common public with the secret. So this is going to be some mathematical operation. What mathematical operation, we'll discuss that, and you'll do a worksheet involving that. But you want it to be one that can't be undone easily, i.e. one that you can't break apart and find M and K. All right, Bob's going to do the same. He's going to take M and he's going to combine it mathematically with his private key in some way, shape, or form. They then exchange those numbers. So Alice sends hers to Bob, Bob sends his to Alice, and then they do the exact same thing again. Alice takes what she received from Bob and she throws her private key onto it. Bob takes what he received from Alice and he throws his private key onto it. At the end of the day, they have the same thing. Whoops. They have the same number. All right. That's their common secret key. But as I mentioned, the thing is that it has to be difficult to recover K from knowing whatever M star K turns out to be. All right. So let's look at a mathematical example. All right, so we're going to start with some common information, namely a base value and a modulus value. The base value is going to be 101. The modulus is 7919. All right, everybody knows this. Alice and Bob know it, and anybody who wants to listen in can know it. That's fine. All right, once that's done, Alice chooses a secret key. In her case, it'll be 29. Bob's going to choose a secret key. In his case, he decides he wants a larger number. He's going to take 1,583. And now they start using the exponential cipher. Alice takes that common base, 101. She raises it to the 29th power, her secret number, and she gets 6301. Bob does the same thing with his secret number. He takes 101, same base, raises it to the 1583, reduces it mod 7919, and he gets 3,796. All right. With those computations done, they exchange the numbers. Alice sends 6301 to Bob. Bob sends 3796 to Alice. So now Alice has 3796. So she raises that to her secret key. And she gets 5810. Bob's going to do the same thing. He's going to take 6301 and he's going to raise it to the 1583. So what he got from Alice, he raises to his secret key, he reduces it mod, and he gets the same thing. He gets 5810. They are now both in possession of the same common number. Okay, so this does it. This is what the Diffie-Hellman exchange procedure is. All right, there's a piece of public information, the modulus, n, and the base g. So in our previous example, that was 101 and 7919. They could be anything pretty much. All right, but everybody is free to know those two numbers. Alice chooses a secret exponent we shall call k sub a. Bob does the same thing, we'll call his k sub b. All right, now they start computing. Alice takes the common base g, raises it to her secret number, reduces it mod n, sends it to Bob. Bob computes that same common base, raises it to his secret number, reduces it mod n, and he sends it to Alice. All right, Alice is now in possession of g to the kb. She raises that to her secret number, and by, nice exponential properties, this total result is the same as taking g and raising it to the ka times kb. Bob does the same thing. He's in possession of g to the ka. He raises it to the kb, and that's the same as net effect g raised to the ka times kb reduced mod n. So that's their common secret key. G to the ka times kb. Now, at no point did either of them learn what ka times kb was. Okay? They received something raised to one of those two numbers, but they never received the individual numbers. More to the point, even if Bob does have g raised to the ka, he cannot find k sub a by the discrete log problem. He runs into that same problem. If he tried to solve it for k sub a, there is no known fast way to do it. All right. So just another quick example. All right, so again, we'll take n to be 541 in this case, and a base of 29. Ka is 67, Kb is 279. Alice computes 29 to the 67th. Bob computes 29 to the 279th. They exchange those numbers. So when Alice receives 294, she raises it to the 67th. She gets 497. Bob does the same thing. The procedure works. All right. And that final number is their common private key. Now, this spring, we find ourselves in a unique situation. There are plenty of times in this class when I give people the opportunity to do little worksheets and maybe the projects where you kind of experiment with these things. Well, we're now really in the situation that this thing was designed for. We are spread across Virginia, possibly further. I don't know if we have any out-of-state students in the class. If so, let yourself be known. And we're communicating over open networks. Okay, so if we want to communicate securely, we need secret keys. And we cannot get together we can't meet in my office and come up with a number. We just can't. All right, so we're going to do this. All right, this is the information we're going to use. We're going to use a base, G of 127, and a modulus, N of 3571. Now, these keys are going to be for communication between you as an individual student and me as the professor. If you want to do an exchange with your fellow classmates, you're more than welcome to. In fact, I'm probably going to make you to. But we'll start out. Okay, every one of you is going to choose a secret number. We'll call it K. Keep it secret. Can't stress that enough. Now, that number K should be less than the modulus, so it should be less than 3571. If it isn't, it doesn't make any difference. It'll just get reduced mod something or other. It's based on the Euler phi of 3571. But you should choose something smaller than 3571. All right, so you choose that secret number. What you're going to do is you're going to compute 127 to the K mod 3571. So you're going to want to use Mathematica. You're going to want to use the power mod command. So, power mod 127 K 3571. Great. That's going to give you a number. Publish it to the Google Hangout. It's an open network. Anybody in the class can see it. All right. But your value K is going to remain secret. All right. In return, I want you to compute 3089 and raise it to the K mod 3571. This is my part of the communication. I have a secret number. I raised 127 to that secret number, and this is what I got. And I am letting it out there. You're going to take the number I've given you, 3089, you're going to raise it to your private key, reduce it mod 3571, and that number will be the secret private key between you and me. All right, you're going to need that number. Do not lose it. I am going to make this a problem on the next exam. You're basically just going to have to present that number on the exam, but I should be able to see it. All right, so I'm going to give you, you're going to have that private key. You're also going to get another one when we talk about what's called the RSA algorithm. But let's see how this works. All right, I am going to call it there. When I talk with the class via the Google Hangout next official time, we can go through a couple of these examples on the fly using Mathematica and the like, and you'll see how it works. But in the meantime, please contact me if you have any questions, and I hope everybody is staying healthy.